Hello everyone. Today we are going to do the last topic in module 3. It is elliptic curve cryptography, okay, or ECC. In short form, you can see sometimes in the question papers that it's written as ECC. Okay. First, the whole of the lecture is divided into two sections. One, we're going to look at what elliptic curves are. Okay, so I'm going to introduce elliptic curves and how addition is done in some operations that are done in elliptic curves. And then we are going to look at how elliptic curve is used in cryptography. Okay, so I will be teaching you elliptic curves with respect to cryptography and security. Okay. First, let's look at what is the motivation of elliptic curve. Okay, elliptic curve itself is not a crypto system. The concepts of elliptic curve is used in other crypto systems, like in discrete logarithm problem or in Diffie-Hellman and things like that. Okay, so we are going to look at what was the motivation. Okay, the problem was that in asymmetric that is PKC methods like RSA or El-Gamal or Diffie-Hellman, we required exponentiations in integer rings and fields. Okay, so rings and fields were used, and large numbers with parameters more than 1000 bits. So the effort of computation on the CPU with 32 bits or 64-bit arithmetic was high. Okay, so the parameters large size, okay, was also critical for storage on small or embedded systems. Okay, so this was one of the problems. So the motivation is in using elliptic curves, we can implement PKC with much smaller field sizes and provide equivalent security. Okay, so that was one of the motivations. Now, elliptic curve cryptography uses a group, a cyclic group is used instead of integer rings for cryptographic schemes with coefficient size. Earlier, it used to be for integer rings, we saw it was 1024 bits. Okay, but here around 160 to 256 bits is more than enough to give comparable security, and that is why significantly the computation effort has decreased. So this is the motivation of using elliptic curve, and many of the security schemes that is used now uses elliptic curve. Okay, now we are going to look at computations on elliptic curve. Okay, now elliptic curves, you can see on the right hand side, this is the shape that you will have for an elliptic curve. Okay, we're going to look more about it. Elliptic curves are polynomials that define points based on the symbol Weierstrass equation. Okay, this is the equation. The equation is y square is equal to x square plus ax plus b, where a and b are real numbers. Okay, they are elements of real numbers. Okay, and this a and b determine the exact shape of this particular curve. Okay, elliptic curves cannot just be defined over real numbers, but over many other types of finite fields. It can be that we can have many other finite fields instead of just R. Okay, but for explanation's sake, we are using A and B as R in our lecture. Okay, now this particular example, you can see the equation is y square is equal to x cube minus 3x plus 3. So A is minus 3 and B is 3 over here. Okay, over R. Now, computation, again, we are continuing. In cryptography, now we are going to look at what is an elliptic curve over prime fields in cryptography. Okay, so we are interested in elliptic curves modulo a prime P. It is not modulo a prime P. Okay, and this particular P value, which we have, that is like, we don't want the values to keep going out of a particular range. Okay, so we will define this P also. Okay, so now elliptic curves over prime fields. Let's look at this equation and I'll explain to you the each point which we don't know. The elliptic curve over Z of P. Now, what is Z of P? Z of, you can see down over here, Z of P is simply a set of integers between 0 and P. So 0, 1, etc. P minus 1 is the set of integers with modulo P arithmetic. Okay, so the elliptic curve will be over Z of P, comma, P is greater than, we will select a prime from this P, which is greater than 3. So the modulo, the actual value which we take, P will be should be greater than 3, is the set of all pairs. So the elliptic curve is the set of all pairs x comma y, which are elements of ZP and which fulfill the elliptic curve equation. Okay, so in our case over here now, we have y square is equal to x cube plus ax plus b mod P. Okay, now it is not over. We have selected a prime and this elliptic curve is within that particular prime. And together, other than this, we also have an imaginary point of in infinity, theta, where a comma b is an element of ZP and the condition 4a cube plus 27b squared is not 0 mod P. This particular equation needs to be satisfied when we select this particular elliptic curve, because cryptographically, this particular equation should be satisfied for the cryptography to be secure. Okay, and there is derivation and all that for this, but we are not going into this. Now, what is this value? Theta. Okay, I'm going to leave it over here for now. It is not exactly theta, it is actually big O. Okay, so for us, we are using theta over here, but you will see in the literature that it is big O. Okay, now this is an imaginary point on infinity. This is actually the identity element. Okay, so to get P, to get minus P, a point P on the elliptic curve, that is why it is x comma y. You have a pair x comma y because a point on this elliptic curve is actually going to have an x coordinate and a y coordinate. Okay, so this particular point P, if there is a value theta, P plus theta, which is equal to P, same, then that theta is the identity element. Okay, so we can see to calculate the identity element, we cannot really, I will show you, after we do addition, I will show you, it's a straight line. So it is somewhere in infinity and that point is defined as theta. Okay, so once again, let's just read this. The elliptic curve over Z of P, where Z of P is equal to 0, 1, etc. P minus 1 with modulo P arithmetic. We choose a P which is greater than 3 is the set of all points on this elliptic curve. The elliptic curve is the set of all points which are elements of Z of P and which fulfill this particular equation together with an imaginary point in infinity theta. Okay, and again, a comma b is also an element in Z of P, and this condition should be satisfied. 4a cube plus 27b squared is not equal to 0. Mod P must be satisfied to ensure security. Okay, now let us look at what is theta. Okay, some special considerations are required to convert elliptic curves into a group of points. Now, what is a group and a group of points? That also we will be looking at. You all have already learned rings and groups. So I hope you know the rules. In any group, a special element is required to allow for the identity operation. There are 5 rules. Please go and look them up. Okay, there are 5 rules. Out of those 5 rules, one rule is that there should be an identity property to satisfy this equation. Okay, so now look over here. Actually, in this equation, we can rewrite it as P minus P is equal to theta. Okay. And now later on, you will see that P, if you have 2 points, then the addition of those 2 points is connecting those 2 points and extending it so that it cuts the elliptic curve in a particular position. But here you can see it is almost straight. So here, if it needs to be cut, then it will be cut somewhere in infinity. That point in infinity is called theta, and that is the identity element. Okay, this particular point is an imaginary point which is not on the curve, but it is added to the group definition. Okay, and it is denoted by big O, or here in this case theta. Okay, elliptic curves are symmetric along the x-axis. Now, one more important point. One, we have discussed theta. Now we are looking at what is an inverse. Okay, so elliptic curve are symmetric along the x-axis. Okay, so if you see over here, if you have a point P, the inverse of the point P is the same. You just drop a line perpendicular to the x-axis, and you will see that the point where it cuts on the opposite side, that is the inverse. So we can see up to 2 solutions. If you take any particular x on the x-axis, you will see there are 2 solutions for y. There will be a y positive and there will be a minus y, which is negative. Okay, how do you know that? You look at this equation. Take any particular x value, substitute the x values over here, and you will get it is y square. So it will be square root. When you look at square root, you have plus or minus some particular value. Okay, so y will be equal to plus or minus one particular value. Okay, so that is how you have, for any particular x, you have 2 points, plus y and minus y on the elliptic curve. Okay, now look over here. The coordinates of P is some x and the corresponding y. Okay, and this particular P also, the x point is the same, but the y point is minus y. Okay, so we can see for a particular P, if you want to find the inverse, then it is simply x comma minus y. Okay, remember that it is not just the negative of the point. So you cannot just say minus x minus y. That is that negative of a point of a particular value is different from this particular inverse value. Okay. Now, let's continue. Now we are going to look at how to do addition. Okay, so from the rules of group, you know that they have additive property, associative property, identity property. Okay, 5 properties are there. Please go through that. Okay, so generating a group of points on elliptic curve based on point addition operation P plus Q. How do we do P plus Q? XP, there are 2 points. So over here we have XP comma YP, which is the P point, and XQ comma YQ, which is the Q point. When these two are added, it will be equal to R, which is denoted as XR comma YR. But how do we get this particular point? We will be doing equations are there. Geometrically, this is how we do it. If there are 2 points P and Q and we want to find out P plus Q, we simply draw a line joining P and Q and extend it so that it cuts the elliptic curve along the x-axis at a third point. Okay, and the mirror of that particular third point symmetrically on the opposite side of the elliptic curve is the additive point. Okay, so excuse me. I just want to show you. This is the point. Okay, so you see this is the point addition. But if this is possible only if P and Q are different values. Okay, two different points. But say we want to do P plus P. In that case, we draw the tangent on that particular point in the elliptic curve and it cuts at a third point on the elliptic curve. Once again, you do find the mirror image on the opposite side because the curve is symmetric, and that point is 2P. Okay, so we look over here, draw a straight line through P and Q. If P is equal to Q, use tangent line instead. Okay, mirror the third intersection point of the drawn line with the elliptic curve along the x-axis, and that is the additive point or doubling point. Okay, but we can't do this in our computer systems. We need calculations. Okay, so now we are using the line equation and finding using the slope. Line is y is equal to mx plus c, where m is the y-intercept or the slope. Okay, so using that equation, we can find the third point. So to find the third point, x3 and y3, when we add x1 comma y1 comma x2 comma y2, then we have these two equations. To find x3, we use s square. S square is the slope. So s square minus x1 minus x2 mod p. Okay, equation can be derived. You just need to use the line equation and you will be able to derive these values. Okay, so s square minus x1 minus x2 mod p, and y3 is equal to, we need this s value, s into, this is the line equation. Okay, so s x1 minus x3 minus y1 mod p. Okay, so these two equations are used to find the third value, the additive point, x3 comma y3. But there is a small difference if p and q are not the same and if p and q is the same. Okay, so the slope is equal to, if p and q are different, we know what the slope is, y2 minus y1 divided by x2 minus x1 mod p. Okay, but if p is equal to q, then s will be equal to 3x1 square plus a. So here the line equation is used to find s if p is equal to q. So 3x1 square plus a divided by 2y1. Okay, once we know the s value, we simply substitute the values over here in these equations to get the additive points. Please remember this equation, write it down somewhere because we need these equations for our later calculations. Okay, now we are going to look at an example of doubling. Okay, so it is given, and this particular elliptic curve is what we are going to use throughout our further explanations. Y square is equal to x cube plus 2x plus 2. So here a and b are 2 comma 2. A is equal to 2 and b is equal to 2. P is equal to 17. So mod 17 is used. This P is the generative point. Generative point means the first point from which we calculate our other points on the elliptic curve. So we are, capital P is equal to 5 comma 1. This point is on the elliptic curve and we can calculate other points on the elliptic curve using this particular point, which we're going to look at in a bit. Okay, so y square is equal to, this is given to us. Now the problem is to compute 2p. So we want to compute p plus p, 5 comma 1 comma plus 5 comma 1. It is not 10 comma 2. Okay, we have to use the equation. We saw if p is equal to q, that means these two are the same, then the equation that we wanted for s is equal to 3x1 square plus a divided by 2y1. We know x1 is equal to 5, y1 is equal to 1, and a is equal to 2. So substitute the values, and these are all modular arithmetic and inverse operations. Find out the divide operation will become 2 into 1 inverse when you put it up. So 2 inverse mod 17 is equal to, the positive inverse is 9. Okay, So this will become 9. And here 3 into 5 square plus 2 is also equal to 9. Okay, so 9 into 9 is 81. 81 mod 17 will give you 30. Okay, now once we have found S, then everything has become simple. Just find x3, plug in the values of S, x1 and x2, and you will get 6 mod 17. And then using x3, you can find y3 with again plugging in the values of S, x1 and x3, y1. Plug in the values and you will get minus 14. So we take positive values. So we will take, because you remember that the values should be in between 0 to p minus 1. So the value over here will be 17 minus 14 is equal to 3. Okay, so 3 mod 70. The rules, modular arithmetic rules. By now, I hope you know all those rules. Okay, so in effect, we have x3 is equal to 6 and y3 is equal to 3. So 2p is equal to 6, 3. Okay, now, how do we find the points, the other points on the curve? Okay, now one thing to note is that elliptic curve is a cyclic subgroup of a particular group. Okay, so what does it mean, cyclic subgroup? After a particular, there are a set of numbers in this particular elliptic curve, points, a set of points, and then after a particular point, you see that these points itself are repeat. Okay, so it is cyclic. Okay, so over here, we already saw how to calculate the addition of 2 points. So use those equations and you can calculate. We saw 2p is equal to 6, 3. To find 3p, we do 2p plus p. So here p and q will be different. So use those equations and we find 10, 6. Then we find 4p, 5p, 6p, 7p, 8p, 9p, all are different values. Okay, up to 19p. When you come to 19p, we see that when you solve the equation, you will find that this value is p minus p. So when it becomes p minus p, we already saw that we have an element called the identity element or the infinity point. So that is theta. Okay, once this particular value is calculated, theta is calculated, then you see any point that comes after that will repeat this particular sequence. So 20p will be equal to 2p, 21p will be 3p, 22p will be 4p, etc. Okay, and these points are the points which are on the cyclic, on the elliptic curve. And since there are 19 points, including the imaginary infinity point, the cardinality of this particular elliptic curve is 90. It is denoted as hash E or cardinality. Okay. Now, how many points can be, roughly, how do we calculate? Exact point, if you want to calculate, we have to do these one by one addition, and we need to see where the point theta is being reached. But there is an equation given by Hass's theorem over here, which tells us the upper bound and the lower bound. That means the range in which we can find the cardinality hash. Okay, so that equation is given by p plus 1 minus 2 root p. This can be derived, but we are not going into the derivation. And so the value is between p plus 1 minus 2 root p and p plus 1 plus 2 root p. Okay, so over here, since 1 minus 2 root p, that is the value of root p, is small, very small compared to p, 1 minus 2 root p and 1 plus 2 root p can be negligent. That is why we interpret over here that the number of points is very close to the prime p. And we can see over here that where our p value was 17, the number of points was 19, which is very close to 17. Okay. And The example is to generate a curve with about, in our case, when we do elliptic curve cryptography, the number of points is normally 160 to 256. Okay, so if we have to generate a curve with about 2 raised to 160 points, a prime with a length of about 160 bits is required. Roughly 160 bits will be required to get a point with 2 raised to 160 points. Okay. Now we are going to the security aspect of elliptic curves and how it is used for Diffie-Hellman or discrete logarithm problem and things like that. Okay. Now look over here. Crypto systems rely on the hardness of the elliptic curve discrete logarithm problem. Now, what is the discrete logarithm problem? Look at this definition. Elliptic curve discrete logarithm problem, also termed as ECDLP. Okay, in short form, ECDLP. Given an elliptic curve E, we consider a primitive element, capital P, and another element, capital T. These are points, okay, P and T. The DL problem is finding the integer small d, where this small d is a number in between the 1 and the cardinality, such that when P is added D times, that is dP, we get T. And you can see that this T is the public key, will be the public key, and the small d is kept private. Okay, so if it is possible to find D from dP, that is from T, only then this can be broken. Okay, but this is a hard problem. To find this D from T is a hard problem. Okay, now crypto systems are based on the idea that D is large and kept a secret. So attackers cannot, compute the D easily. T is publicly known. If D is known, but at the same time, if this D is known, that is, if I know my private key, I should be able to calculate dP. To create that, if I know the private key, I should be able to calculate the public key and disseminate it. Only then I will be able to use the crypto system. Okay. Now to calculate this, if D is known, an efficient method to compute the point dP is required to create a reasonable crypto system. And that is done, if you remember the square multiply method, that method is adopted. In that case, we were doing square multiplication was the base operation. Okay, so we were doing square and multiply. But in elliptic curves, addition is the base operation. So we will do doubling, that is P plus P, and addition. Okay, we will be adding P to the method. Everything else is the same. We are going to look at an example. Okay, the method for efficient point multiplication on elliptic curves is double and add. Okay, now let's look at, this is the pseudocode. Let's look at this example, and then you can look at the pseudocode. You will understand it perfectly. Okay, supposing I want to find 26P. Okay, now this particular point P is a point, so it is XY coordinate. Okay, so to find 26P, just like we do in the square multiply algorithm, you find the binary of 26. So we have 1, 1, 0, 1, 0. Okay, so there are 1, 2, 3, 4, 5 bits. So it will take 5 steps to calculate 26P. Okay, 5 steps in the algorithm. Okay, so now the first step is always beginning with P. Okay, so P is equal to binary 1P. Okay, now the first, after that, what we do is we do double and add. So double is P plus P, which is equal to 2P, and in binary it will be 10P. But if you look over here, the second digit is not 0, it is 1. So what we need to do? We need to do an add also. So we will do 2P plus P, which is equal to 3P. Okay, so 10p plus 1 will give you 11p. Okay, and now we can see that the first two digits are correct. Okay, now the next step is again a doubling. So we will take the previous element 11p plus 11p, which is equal to 6p. That will give you 110p. Okay, and if you look, this third element is 0, so nothing more needs to be done. In the next one, again, we will do 6p plus 6p. We will get 12p, which is equal to 1100p. But we need a 1, not a 0. So we need to do an add also. So in the next step, we get 1101p. Okay, then after that is over, again, we need to do the next doubling. Okay, when we do doubling, we get 11010p. And now there is no need for an add because the last bit is 0. So we look just like in the square multiply, we look from left to right, the multiplication bits. Whenever there is a 1, we need to do a double and add. When there is a 0, only a double will be done. Okay, and we finally, in these many steps, 1, 2, 3, 4, 5, 6, 7. In 7 steps, we have got the result of 26p. Okay, so this is how the multiplication point dp is calculated using an algorithm called double add algorithm for elliptic curves. Now we are going to look at everything, all the different components are put in place, how to do addition, how to do the multiplication, how to find the points, all these things we have done. Now we are going to see how it is used for cryptography. Okay, so the basic algorithm for, we are looking at how elliptic curve is used for Diffie-Hellman, but the basic algorithm for Diffie-Hellman is the same. Only thing, the values we are taking from the elliptic curve. So the points are on the elliptic curve. Okay, so the first thing, we are given a prime P and a suitable elliptic curve. There are standard elliptic curves from which we can choose. Okay, and the prime value we can choose, it should be between 1 and the cardinality of E. So we can choose as we wish. Okay, and secure prime values are also known. Standard values are provided by NIST. Okay, NIST. So given a prime P and a suitable elliptic curve E and the generative point XP, YP. Okay, so these three things need to be given. The elliptic curve Diffie-Hellman key exchange is defined by the following property. First, Alice chooses her private key, which is called KPRA. And this value must be between 2 and cardinality minus 1. Okay, so if you remember, P value is between 1 and E, I mean hash E, but here that A value must be between 2 and any value from 2 to hash E minus 1. So an A value is chosen. From using this A value, A capital P, XP, YP, the generative point, AP is calculated. So this is a point on the elliptic curve. Capital A is a point on the elliptic curve. So the public key is calculated. Alice's public key is calculated as AP, which we looked at. The algorithm is double add. Okay, so XA, YA is then sent to Bob. This is A is the public key. Bob does the same thing. He chooses a private key for himself with the same rules, and he calculates his public key using BP, and he sends XB, YB to Alice. Then what Alice does is she takes Bob's public key and multiplies it with her private key, and she gets TAB. And Bob does the same, takes Alice's public key and multiplies it with his private key and gets TAB. Now, TAB is the session key. Okay. Now, this session key can be used with any symmetric key algorithm like AES or whichever, triple DES or whichever, and they can securely transfer messages. Okay, so a joint secret key is generated XAB, YAB, the proof of correctness. Alice computes A, capital B. What is capital B? Small b, that is private key of Bob, into the generative P, which is equal to ABP. Similarly, BA is computed by Bob, and that is BAP, which is also because these points are associated. So ABP, since group is associative. Group, remember the rules of group. I told you earlier, it has associative property. So now both Alice and Bob has got the same key. Now, normally, remember that this is a point. TAB is a point. So to use the key, the X coordinate is normally used. So XAB, the X coordinate, is normally used as the session key. And sometimes this XAB is once again hashed, and the hash value is used as the session, okay, in some cases. Now, as I told you, how exactly after exchanging the key, messages are sent. It's very simple. This XT value, both Bob and Alice has got the XT value. The XT value is taken, in this particular case, AES is used. So XT value is taken as the key of AES. So the key of AES is KAES, and the message is encrypted using the AES algorithm using this XT value, and it is sent. Sometimes this XT value is once again hashed, and then that value is used. That's all. So here, encryption is done. Okay. Now, what is the security? Okay. Now, in the case of elliptic curves, we saw earlier that the size of the parameters are significantly decreased. 160 to 256 bits is used, whereas in RSA, we required 1024 to 3000 bits. Okay. So the reason is that attacks on groups of elliptic curves there aren't, very strong attacks. They are weaker than the factoring algorithm or integer discrete logarithm attacks, which are possible on other systems. Okay, the best known attacks are baby step, giant step, and Pollard row method. Okay, and for any attack, roughly root of P steps are required before the ECDLP can be successfully solved. Okay, so 160 bits becomes sufficient. Okay, now we are going to look at the implications of this particular, size. Okay, when an elliptic curve uses a prime with 160 bits, roughly 2 raised to 160 points provides the security. Okay, and to break this, root P steps are required. Root P steps means when it is 2 raised to 160 points means 80 steps. If you remember the, bit arithmetic, then divide by 2, 160 divided by 2 is root P. So 2 raised to 80 steps are required for an attacker to solve this ECDLP problem. Okay, and research shows that 2 raised to 80 that is 80 steps means it will take 3 or 4 years to compute this particular value, which is not practical. Okay, and if the number of bits is 2 raised to 56 steps, then 2 raised to 128 steps is required to break the ECDLP, to successfully solve the ECDLP problem. Okay, so this is how we are showing that elliptic curves are secure. Okay, with advancements in hardware and computational facilities, this will change. But till then, elliptic curves are secure. Okay, now we're going to look at implementation. Elliptic curve cryptography is implemented both in hardware and in software. And the computations, if you see, are normally done in 4 layers. One, we require modular arithmetic. Another, we require group operation. And we require point multiplication. And the uppermost layer is the protocol. Okay, so either the Diffie-Hellman protocol for key exchange or encryption for the purpose of encryption, or digital signatures. Okay, so these are the 4 operations that are required for elliptic curves. Okay, and the most effort is required for modular operations. Okay, so that is why this is at the bottom of the layer. Okay, now the software implementation is slightly less, what do I say, efficient, but still much better than any other algorithm. So optimized 256-bit ECC. 256-bit ECC means we are taking the upper bound. So the number of bits that we are using is 256 bits. Implemented on a 3 gigahertz 64-bit CPU requires 2 milliseconds per point multiplication. Okay, and in less powerful microprocessors like smart cards or cell phones, it might require greater than 10 milliseconds. Okay, so this is the software implementation, but in the hardware implementation, it will take as few as 10 microseconds. Okay, so high performance implementation of 256-bit, if it is 256-bit special prime, can compute a point multiplication in a few hundred microseconds, and dedicated chips, if it is used for ECC, then the point multiplication can be computed as fast as 10 microseconds. Okay, so the implementation is possible in both hardware and software, and it is quite efficient. With this, we complete module 3 and elliptic curve cryptography. As usual, feel free to contact me if you have any doubts. I will put the link of a little more detailed explanation of elliptic curve if in case you feel that you want, the explanation of Professor Christof Paar. And feel free to contact me if you have any particular doubts. And don't forget to like and subscribe. Thank you so much.